Okay, so good afternoon, everyone. It is my pleasure to present this presentation on reactive gases in a changing atmosphere, global observation, data assimilation, and services. And we have been learning a lot about the history of what BIRA has been doing in the past. And in this presentation, I will more specifically concentrate on the present more than on the past, and to some extent also on the future. So this is the outline of this talk. I will talk about a brief introduction concerning atmospheric reactive gases, then present stratospheric ozone research and work we do at BIRA on data assimilation and related services. Then I will go down in the atmosphere and focus more on work we do on global tropospheric gases monitoring from space instruments. Then I would like to emphasize a little bit the role of ground-based network in support to space observations, and finish by some work on the work we do on quality assessment and validation in support of these atmospheric composition observations. Atmospheric processes, so this is a nice overview I took from the internet, and it may look a little bit complicated at first glance, but maybe we can make it a bit easier. So if we are talking about atmospheric gases, the first thing to take a look at is where do they come from? Of course, to some extent, there are some emissions higher up in the atmosphere due to airplanes or also due to volcanoes, which are not represented on this graph. But as you can see, most of the emissions in the atmosphere actually take place at the surface. And these emissions can be either of natural origin, like, for example, oceans, which are emitting desert dust, agriculture. You can find vegetation. It's also, as we learned this morning, quite important. There are also, of course, anthropogenic emissions related to cities, industry, or transportation. So once emitted in the atmosphere, gases and particles can have some history in the air. And of course, if they are very reactive gases, they tend to stay very close to the surface and where they undergo chemical transformations. So those species which are a bit more stable, they tend to be transported in the atmosphere higher up by diffusion and also by winds. And they will be transported at longer distance where they might undergo some chemical transformations. They can also be trapped in clouds and then washed out by rains, ultimately. So the most stable will actually smoothly and slowly go up into the stratosphere, and there some of them might ultimately be again fertilized by the strong UV radiation and also undergo chemical transformation, and this is the process leading to ozone destruction, for example. So this is the overall picture. I would like now to discuss a little bit more about reactive gases. So reactive gases, they are very diverse. There are lots of them. And here I only took a selection of one of the important ones, at least those that can be measured by ground-based or satellite remote sensing techniques. And I would like just to explain a little bit how they are interconnected and the link between these species. So as I said, emissions are mostly taking place at the surface. And because reactive gases are reactive, they tend to be located, most of them tend to be located close to the surface, and there you are not surprised to learn that they will have an impact on air quality. And of course, some of these species are toxic on their own, but they can also react with each other or with particles to actually create ozone, which is at the surface a very important pollutant, as you know. Now, ozone, as you also know, is also formed higher up in the atmosphere, in the stratosphere, at around 20 kilometers of altitude. And in this region, it is good. It is protecting us from the solar radiation. But again, as we learned today, at this altitude in the stratosphere, there are also reactive gases which will control the amount of ozone. And we know that, for example, that halogens are very important in controlling the ozone concentration, and they are actually responsible of the ozone depletion and ozone hole like explained earlier today. Now, volcanoes are also important in the atmosphere because they are emitting gases and also a lot of particles in the atmosphere. And actually, volcanoes are the biggest source of sulfur in the atmosphere. And because SO2 is usually emitted together with ash and particles, this can also have some impact on aviation. And I will come back to this a bit later in this presentation. So ozone, because ozone is absorbing radiation, this is why it is protecting us. It has also, of course, an impact on climate. So ozone is related to climate, but because the ozone concentration is also controlled to some extent by a number of precursor particles, or precursor molecules, there is a clear interaction through the chemistry between climate and air quality. And ozone is, I think, a nice molecule to explain a little bit the relations between chemistry and climate in the atmosphere and the interaction. So as we know, ozone is protecting us by blocking the high energy UV radiation from the sun. So this is a good ozone layer. And in the troposphere, as we know, it is bad ozone. It is a pollutant. So ozone is absorbing radiation. It is actually the most important radiatively active trace gas in the stratosphere. And for this, it is considered as an essential climate variable by the GCOS. So what is interesting is to think about also the evolution of ozone in relation to climate. So this is a slide I took out from the last WMO ozone assessment report. And it is, I think, quite illustrative. It is showing the time evolution of the ozone change. And it is compared to the time evolution of the equivalent effective stratospheric chloride, which is actually a good proxy for the halogen-induced ozone depletion in the atmosphere. And you see that the maximum peak here in halogens coincide with the minimum here in the ozone. So this is total ozone column for the mid-latitude. So in blue, you have observations, and in shaded area, these are simulations and projections actually for this century by chemistry transport models or chemistry climate models. And I think the interesting things here is that you see that there is quite a lot of uncertainty and quite a big range of possible projections. And the reason is that not only the content in the halogen is reduced in the stratosphere, but also the climate is changing. And because the climate is changing in this century, we expect that there will be change in the temperature, change in the atmospheric dynamics, and this change will impact the ozone concentration. And these simulations was actually made for 4 different scenarios, going from the most optimistic to the most pessimistic situation. And you see that for the most pessimistic situation, so in case of continued increased, so business as usual without any change in the emissions, we expect that, of course, the temperature of the Earth will increase quite a lot, and this will have a positive impact on the ozone. So we will have projections in average tend to predict a super recovery of the ozone due to the climate change. Okay, so clearly it is very important to monitor the evolution of the ozone layer, and it is very important to understand how ozone has been changing over the past. And this is one of the motivations of the Ozone CCI project, which is an ESA project from the ESA Climate Change Initiative. So the ESA Climate Change Initiative is a program launched by ESA about 3 years ago. It is focusing on establishing 13 essential variables, one of them being ozone. And BIRA is responsible as leader of this project. So the focus is really on developing state-of-the-art ozone climate data records from a quite large number of sensors, basically all relevant European and ESA-associated sensors. And in this project, on top of coordination, BIRA is responsible for the development of the total ozone level 2 climate data record. It's also playing an important role in the coordination of validation tasks. And of course, this project has been already running for 3 years. We are in the second phase of the project, and this is one of the important achievements obtained after the first period of 3 years. So we have been able to create a new high-quality consistent data record from 3 ozone sensors, all processed with the same kind of algorithm and advanced corrections to really make them as much as possible consistent with each other. This data set has been recently published, and it is used for level 3 dataset generations, some regional trend analysis, assimilation in atmospheric reanalysis model, and other applications. And this is just one example of applications. Also, recently published paper by Coldaway et al., which is showing an analysis of ozone trends regionally distributed. And it's quite interesting to see patterns in the trends that can be related to dynamical effects or chemistry effects. Okay, so measuring ozone is very important, but of course, if you really want to understand how ozone is related to other reactive constituents and how it is coupled with the dynamics, it is really essential to be able to modelize this. And at BIRA, we have developed the BASCO chemistry transport model, which was actually initiated by Dominic a few years ago. And this model is a quite advanced model which is dealing with chemistry in the stratosphere. It has all these specifications, transport by wind and temperature are actually taken from meteorological center, which means they are very realistic winds. And based on this model, BIRA has been developing the assimilation system, the BASCO assimilation system. So this slide is illustrating the principle of the data assimilation, which basically consists in optimizing a model state. So this is an initial state of the atmosphere only based on modelization. Then you try to fit this model with observations, and as a result, you obtain an assimilation field. So this assimilated field is to some extent the best representation that you can expect from the atmosphere, combining observation and a priori knowledge on the atmosphere from the model. Different methods are developed, including 4D VAR and ensemble Kalman filters, which are statistic approaches, but I cannot really go into the details here. But the fact is that using this model, you can do very interesting things, like looking at the reanalysis of the stratospheric composition. So this is something which has been performed by Quentin Herrera and his team. And here what you see is a comparison between observations by Aura MLS and also MIPAS for a number of different gases which have been assimilated in the system, and then after assimilation compared with the original observation. And you see in blue and in black that the curves are almost on top of each other, which means that the assimilation works really well. In red, you see the original model, so before assimilation, and you see that in some cases, the assimilation is really bringing you quite away from the original model data. So this kind of thing of analysis is very important, really, to understand how the different species are coupled with each other, and also they can bring interesting information on the impact of dynamics on these species, and also how ozone and other species can have an impact on their own on the dynamics. So this kind of tool can also be used in a service mode, and here BIRA has been very active recently, and this is more a work by Simon Chabriat in the framework of the new Copernicus service. So the Copernicus, maybe you heard about it, is a new European system of services for monitoring the Earth. And it is a broad range of activity, but there is an atmospheric component. And this atmospheric component is under preparation, still under preparation at the moment within the MAC project, but soon will become operational in the framework of the Copernicus Atmospheric Monitoring Service, or the CAMS service. So here, BIRA has been quite active and is contributing with validation and also providing a stratospheric ozone service. And this is just an illustration of the web page which has been created and maintained here at BIRA. So we provide comparisons of the model with ECMWF results, also animations of the ozone hole. And this is just to show you one example of the kind of service that can be provided by the system. This is showing you a comparison between the evolution of the ozone hole for this year in comparison to previous year, 2013. And you see that the evolution is quite parallel, not identical. And you will see that the ozone hole for these 2 years tend to develop more or less in the same way. So this kind of simulations can also, of course, be done with other years and other situations, and also for the northern hemisphere, like we saw this morning. Other thing that you can do is to use this reference system to validate other assimilation systems. And here the BASCO has been used has been intercompared with results of assimilation. So this is showing you the deviation with respect to a reference ozone measurement for 3 assimilation systems. So in blue you have BASCO, in green another assimilation system called CECADA, and in red the ECMWF assimilation. And you see that BASCO is performing much better in this case on the ozone analysis, and the main reason is that BASCO is the only model in this case which really focuses on the stratospheric ozone, and it's also making a better usage of satellite data. So this is really a reference. No, okay, I think so far so good for the stratosphere. I would like to go down a little bit into the troposphere, because this is also a region where we are very active in the division. And of course, tropospheric gases, as you know, can be measured using satellite sensors, UV visible satellite sensors, such as GOM Skiamaki and GOM2. Also, tropospheric composition can be very nicely monitored by infrared sensors, for example, IASI, and there is actually a very strong expertise in Belgium on this, but here I will really concentrate on UV visible satellite sensors, which are really our specialty in the division. So these measurements allow for global monitoring of several very important air quality gases, such like nitrogen dioxide, SO2, formaldehyde, ozone. And BIRA has developed over the year a strong expertise on such retrievals through participation to successive missions since the late 90s. Doing this, we collaborate strongly with international partners. I cited these partners, but there are many others. And also, I would say that the main focus in the team is really to work on trying to build long series of consistent data from multiple sensors. And this can be used as an input for models, trend analysis. We'll try to illustrate a little bit. So what are we talking about? We are talking about satellite observation. And these are not limb sensors, these are nadir sensors. So we really look down to the troposphere at the vertical. And at the moment, the sensors that can be used to do such kind of monitoring are in sun-synchronous polar orbits. So this is showing you an illustration of the way it works. So we have been starting this kind of observation already in 1995 with the GOME instrument on ERS2, which was the first nadir sensor being able to measure the tropospheric composition. This was continued with the Skiamaki on Envisat. And then we are, since 2007, strongly involved in the GOM2 METOP mission from EUMETSAT. METOP-B has been launched 1 year ago, and METOP-C will be launched later on. So all these systems are scanning spectrometer, which means they look at nadir and they scan like this over a swath to obtain a global coverage. So OMI on Aura is a little bit different. One reason is that it is not using a scanning technique, but an imaging technique. So this is a push broom technique, which is a bit different from the scanning, and it's also in contrast to the others flying in the afternoon. All the others are flying in the morning, which means this instrument can sample a species at a different time in the day. So different photochemical situation, different situation with respect to emissions. So the future is actually the TROPOMI sensor on Sentinel-5 precursor. So TROPOMI is in a way, an improved version of the OMI instrument with a much stronger focus on the troposphere than OMI. So TROPOMI is an instrument developed in the context of the Copernicus Sentinel program. It is a Dutch instrument operated on the ESA platform Sentinel-5 precursor. And it is also using an imaging technique. And really the nice thing with this instrument is that the resolution will go to a 7x7 unprecedented high resolution of 7x7 square kilometers. which will bring a lot of interesting new things. And I will try to illustrate a little bit of this. So what can we do? What can we obtain with this kind of satellite? This is showing you an animation of basically probably the best product you can obtain at the moment, which is for the troposphere, which is based on the OMI instrument. This is an average over the period from 2005-2010. So this is an average over 5 years of observations. And NO2 is actually mostly emitted in relation with anthropogenic activities. It is strongly correlated with density of population, industrialization, and also car traffic. And if you look into the details, you will see that all places where you have big cities, high industrialization, correlate very nicely with the NO2. So this kind of global map is really very interesting because it allows you to pinpoint emissions globally. It also allows you to look at trends, variations in these emissions, to verify whether emissions provided by countries are real or not. There are a lot of things that can be done. China is, of course, very strong hotspot, like you may expect. And I think the animation is finished. Another interesting gas is formaldehyde. So formaldehyde is different, and you see that the pictures, the emissions have a different nature. And this is mainly because formaldehyde, which is a volatile organic compound, has also, in contrast to NO2, a lot of natural sources. It is emitted in large quantities by vegetation. It is also produced in large quantity by biomass burning. And you see these very strong emissions here in Africa, which are not due to pollution, but really due to these natural emissions. And if you go in Europe, you see most of these emissions are natural, but there are places where pollution is also playing a significant role in the emissions. And if you go, for example, here in India, this is quite interesting. You see that you have a lot of natural emissions or related to vegetation, but here you have a very strong density of population and also an accumulation of these species because you are just at the reach of the mountain. So this is the Everest, of course. And again, China, very strong emissions, both due to natural processes, but also a lot due to anthropogenic things. And here we are in the United States. Most of these emissions are related to isoprene, which is a strong natural emitter of volatile organic compounds. Okay, what can we do with this kind of observation? I cannot go into all the details, but one very important application for such tropospheric observation is to constrain our knowledge about the emissions. So we have some knowledge about emissions which are derived from knowledge at the ground. And it is quite interesting to try to confront this knowledge to what satellites are telling us. And there will be more details about this in the following presentation, so I don't want to go into the details, but here the idea is to start from a model a priori simulation of the formaldehyde in this case, and then to confront this with observations in an inverse scheme to derive optimized observations, optimized column, and this is telling you, this is used to tell you some information about the emissions. You can also look at the time variation, and this is also an interesting study made in our group, looking at the time evolution of the formaldehyde. And here you see that this is the average over the last 10 years. You see that there is a positive trend here in Asia, while in Europe and in the United States you tend to see a negative trend. So these trends are mostly related to changes in the anthropogenic emissions and not so much in the natural emissions. Maybe one difference is Amazonia here, where the change is probably related to deforestation and probably the associated change on the evolution of biomass burning. This is still under discussion at the moment, but I think these are very interesting results. Now you can also use this observation to go into services. And how much time do I have? 5 minutes, okay. So this is the support to aviation control service. So here the idea is to use satellite observation to provide information to the public. And as you know, volcanoes emit ash and gases in the atmosphere, and this ash can be quite harmful for aviation. So here the idea of the service is to use observation of SO2 and volcanic ash, which can be detected using UV vis and thermal infrared sensors to provide a quick and also accurate information, or I should say selective information, on whether or not a volcanic eruption has been taking place. This is based on 7 partners, so it's a strong international collaboration, and we have at the moment more than 200 users, which are volcanic ash advisory centers, observatories, airlines, pilots, Met Office. And the service is actually based on a constellation of satellite instruments, this is represented here, which are all based on sun-synchronous observation, but at different local times, and this is helping us to improve the reactivity of the system. So this is just showing you an example for the recent Kelut eruptions, which took place in February 2014, and an alert was sent less than 3 hours after the start of the eruption. Now I would like to spend a little bit of time, so the last 5 minutes, on the ground-based reference network data. So having satellite data is very nice. This is providing the global picture, but you have to know whether these satellites are trustable. And for this, high-quality ground-based reference data sets are essential for validation. And at BIRA, we have been quite active on this, and especially in our group, well, not only, but also in our group, we have been quite active, and mostly in developing the remote sensing DOAS technique as part of the international NDAC network. So at the moment, we have developed and we are operating 6 and almost 7 stations, which are represented here, which provide columns and profile measurements of all relevant UVV species that can also be measured from the satellite. So BIRA is a major actor in developing the UVV's component of EDAC, so this is a contribution to the NDAC network, and this is also an essential contribution to the preparation of the Copernicus Sentinel program. And I just would like to show one illustration of what can be done. So this is showing you an example of the application of this MaxDOAS observation to satellite validation. So we have been using a MaxDOAS instrument for several years in Xianghe. So this is a Chinese city. This is not, which is surrounded by 3 big cities. It is not really inside a hotspot of emission, but it is surrounded by cities where emissions are very strong. So which means we are not right in the middle of the emissions, so the gradients are not too strong, and this is a quite ideal situation for the validation of the current satellite sensor, which have a limited spatial resolution. So based on the analysis of the data, we can derive, and so these are time series of observations of different gases, all retrieved by the ground-based system, and you can use this observation to compare them with satellite observation. And here, this is just showing you an example of a comparison with the OMI sensor, of which you have seen the results before in the animations. And you see that for NO2, formaldehyde, SO2, it is possible to verify the quality of the satellite data. There is a lot more into this, but I don't have to go into the detail. Another thing which I guess will be very important in the future is to complement the ground-based observation with airborne systems. And actually, imaging those systems on board of aircraft or of UAVs can be very interesting because they allow for high resolution. And when I mean high resolution, it's really at satellite subpixel scale mapping of pollutants. And we are working on developments at BIRA in collaboration with Vito on Apex and Swing experiments, which are one instrument on board of an aircraft, and Swing is a very small compact system operated on board of UAVs that we try to develop to look at this. And just, I would like to illustrate the potential of this. So this is not based on observation by our system, but this is a result very recently obtained as part of a campaign, the Aromat campaign, which took place in Romania, Bucharest, this September. And this is showing you a mapping of the NO2 which was recorded from an aircraft. So the resolution is about 50 meters. And so you can see the scale. This is 30 kilometers to an 18 kilometer in this case. this is showing you the size of a troponin pixel, so this instrument that is going to be launched in 2016. The best, or the most highly resolved instrument at the moment is OMI, and you can see that the size, typical size of the pixel hardly allow you to sample the whole plume. And if you would put a GOM2 pixel on this, it's actually larger than the page. So I think it is quite interesting to see this evolution in the resolution of the instruments, and also that TROPOMI will actually be the first instrument being able to quantify NO2 and other short-lived gases in urban areas. Okay, so last part is it is good to develop systems for validation, but it is also important to use these tools in a quite integrated manner. And efforts are being done by Jean-Christopher Lambert and his team to build a system of validation. And the multi-test system is the most well-known one. So this is an automated, versatile system for validation of atmospheric composition satellite data, which use a combination of different reference data from many different networks and balloons. So this system is addressing the full chain of quality assessment and validation process. And this goes from user requirements analysis up to discussion of compliance with user requirement, and includes a lot of different detailed process. So just one example of how this kind of services have been evolved, have been used in the past. So this can be used to support the evolution in data processing, and this is just showing you in which way the ozone processing has been evolving since 1995 and the early stage of the GOME instrument. So in 1995, this was the first validation of the first version of the ozone product from GOME, and you see that results were really bad. And this has been improved quite a lot with the time. And now we are reaching this very nice level of agreement. This was monitored by this system. And a last interesting development, I think, in the same area is the Osmos metrology simulator. So people in this group are working on developing so-called OSSE, which means Observing System Simulation Experiments. So here the idea is really to build a system that allows you to simulate with as much as possible realistic, in the best realistic way, the observations in a realistic atmosphere. And it's including several components, observation metadata, which help you to describe the observations. Here, observation operators, which describe the volume, weight, and dependency of the measurement sensitivity. So this is telling you in which way the remote sensing data is differently sensitive to different area in the atmosphere. You combine this with realistic simulations of the atmospheric fields, and this can be based on three-dimensional chemical transport results, for example, from BASCO or from EFS Mozart. There are different possibilities. This is giving you a four-dimensional picture of the atmospheric field, and then you can combine everything and try to characterize in which way the observation can be affected by limitations. So on this plot, what you see is a representation of the ground-based observation. In blue, the satellite observation, and in color code, you see the ozone field, and you see that by making an analysis of this, you can infer how much of uncertainty is coming from the fact that what you measure is not the real atmosphere, but the atmosphere as it is seen by the remote sensing instrument. Okay, I'm now moving to the conclusion. So I think I've tried to show that we are developing expertise and strength on several areas in this division. Stratospheric ozone observation and modeling. I think BIRA is a key player in the atmospheric Copernicus service and also in the ESA-CCI program. Tropospheric gases observation. We are very strong in algorithm development, also strongly involved in the preparation of future missions like the Sentinels. QA validation, BIRA has been involved in the establishment of reference ground-based systems and also on the exploitation of these systems for the assessment of existing and will be used for the assessment of the future missions. So for future activities, of course, we want to reinforce where all activities where we have been able to show our strength. So reinforce our role in the Copernicus Atmospheric Service, develop scientific algorithm for sentinels, but also at the same time further develop the ground truthing methods and services which are necessary for future missions, and this also includes airborne techniques. And finally, we also are looking to explore better ways to address the study of chemistry-climate interactions. And with this, I would like to acknowledge my team of the Atmospheric Composition Reactive Gases Division and especially to thank you for your attention.